So what we're going to do today, we're going to talk about power and then confidence intervals on effect size. This is probably one of the most important lectures in terms of concepts, starting to understand the limitations of our methods, and then in terms of also, as our journals are getting increasingly sophisticated, at least top tier journals in clinical psychology, if you want to submit to those journals, you not only should be thinking about you're going to have an effect size attached to stuff, which we're getting pretty good at, but then also maybe a confidence interval around that effect size. And there's some complexities around calculating confidence interval around an effect size that's still kind of murky in terms, you have to dig through a number of different individual papers. What I've tried to do is kind of condense this all here for you all, so you can go through and start including some of this stuff. And then the slides that I added on to this lecture include some examples from stuff that I've done that have tried to make reasonable use of confidence intervals around effect sizes to show you what that might look like in practice. So we're going to first talk about power, factors that influence power. Non-centrality parameters is going to be a big important topic that will come in later. Calculating our a priori power, this is important. Oftentimes our studies will not be adequately powered, but you should at least know that going in, as opposed to pretending that's not an issue. Talk about some problems with stuff that SPSS gives you in terms of observed power, and then why it's difficult to calculate confidence intervals around effect sizes. Thanks to computing power, this has become actually fairly easy and straightforward now, as long as you understand the procedures. It gets back into non-centrality parameters, again with this, and then actually the procedure of going through and calculating some of this stuff. Okay. So, want to start out talking about our different types of error that we can observe within a study. So, typically, with our null hypotheses testing, we're almost always concerned with, or the primary concern with standard traditional null hypothesis testing is with type 1 error. Morgan, what's a type 1 error?
Type 1 error is when there is no effect, but you state that there is an effect.
Right? And this is the thing, right? This is the thing we're all terrified that someone's going to get something that's there that they don't deserve, right? That we're going to say that there's an effect that they should be claiming an effect, right? And this is our type 1 error. And this is the error that is set by what in our hypothesis test? Alpha, right? We set our alpha. We say what's our threshold for the possibility of making a claim that we have an effect when there isn't actually an effect there. What we end up being is typically less concerned about our type 2 errors, right? Sam, what's our type 2 error tell us, or correspond to?
Failing to reject the null hypothesis principle.
Right. If there's an effect out there, right? There's an effect out there to be had, but we fail to reject the null, right? Which says, we're not saying that there's not an effect, we're just saying we don't know, there's not an effect. We don't have, our data is not sufficient to claim an effect in these data, okay? But we don't worry about type 2 error a whole lot. Why might this be a problem? What do you think, Stephanie?
Just hear
well, if there are relationships there, and we are just not detecting them, then we are setting ourselves and our field back.
Right, right. If there's something there and we're not picking it up, right, and we've got a bunch of studies out there that say, oh, we haven't been able to detect this, even if there's something to be there, right? But we're just making type 2 errors, that has the potential to impede our scientific progress, right? What other types of things might be problematic with our type 2 errors?
failing to detect diagnoses.
Yeah, right. Let's say I've got an intervention, and it's a cheap intervention, and it's not anything that's going to cost anybody anything. Side effects are going to be really small, right? And maybe it has a small but reliable effect on some health outcome in the population, right? I'm missing an opportunity to institute a policy that would be cheap, effective, and on the aggregate, very beneficial to people, but if my study's underpowered, I haven't detected that, right? So some things we should definitely be worried about, and I guess from a research standpoint, right? From a resources standpoint, why might it be important to start thinking about your type 2 error in terms of, say you're a new investigator, you're going to put a bunch of money into this study to test this thing. Why might you want to be thinking about type 2 error ahead of time?
Well, if you power your study, then you can figure out the minimum number of people that you can have and still detect something, so you don't have to oversample and stretch your resources.
Okay, so maybe I don't sort of spend too much money on getting people I don't need, right? What else? What's maybe the inverse of that that's problematic? I'm headed on a fool's errand, right? Maybe this is a cool thing, but I'm going to drop, 7 figures on a study that has next to zero opportunity to detect the effect that I'm planning to affect, right? I basically have to land double zeros on the roulette wheel in order to be able to detect an effect of this size in my sample of 20, even though it's going to be, let's say, running people through the MRI, right? That's expensive, right? And so probably want to get a good sense for, all right, what's the effect I'm looking for? How much is it going to cost me? And what's my likelihood of detecting that effect given a sample of a certain size, right? So all these things start to become important in thinking about, and then if you go on to do any type of grant-funded research, right? No one wants to give you money for something that's, a 1 in 100 chance of you finding anything, right? That's not a good investment. So certainly need to be thinking about type 2 errors, but we don't. We typically worry about type 1 error and we just pretend that this isn't happening. Some reasons for this, our null hypothesis test is focused on type 1. Like our whole system is geared towards not making a type 1 error, right? The way our hypotheses tests are set up, our correction for multiple comparisons, worry about alpha inflation, things along those lines, right? Some concerns with just the inherent structure of our scientific procedure puts a focus on your type 1 error. Calculating type 2 error, this is hard, all right? We're going to get into, we've got slick online calculators that seem like they're no big deal now, but historically it's been very, very difficult to accurately calculate this type 2 error, right? Basically you need to get a sampling distribution that's not the sampling distributions we use for our hypothesis test, and so we were limited to a small collection of tabled values to try and get at some of this stuff, and so it's been kind of hard, and then also disappointing conclusions, right? Why might we just be disappointed when we calculate the probability of our type 2 errors? What do you think, Katie?
Because researchers don't really want to conduct research if they know that it's not going to be supported by their data because it won't get published.
Well, oftentimes what happens is we go forward and we will say, all right, this is the study. This is how I want to do the study. This is how many people, or how many people am I going to need to calculate this, or what's the likelihood of making a type 2 error if I run this in my sample of 100 people. Pretty excited about my 100 people, right? And then find out that with 100 people, my type 2 error is still like 0.6, right? Which is awful, right? Basically says, it makes us sad, right? We don't like to see this because it tells us that even though we have this great idea, that oftentimes our level of type 2 error is still going to be unacceptably high, and so then we get bummed out about that, right? And so if we're thinking about, but we should be thinking about type 2 errors, right? Because what we're doing is basically, we're failing to reject the null, and then oftentimes, even though we shouldn't be, the implicit interpretation is that there is no effect here. There is nothing here. when oftentimes, and when we go through and we take a look, our average study in psychology is powered to about 0.5, means about we've got a coin flip on detecting that effect that's there, right? And so this stuff starts to become problematic, so we should think about our type 2 errors. So type 2 error has a direct relationship with power. So if type 1 error is alpha and type 2 error is beta, our power is given as 1 minus beta, okay? This is our power is identified as the long-term probability of rejecting the null given a particular effect size and alpha level. Let's switch things up here quickly. Okay. Transferred the wrong, the not updated slide onto there, and so now we're better. I'm not exactly happy with it all. Sad. But at least we'll have the right slides up there. Okay, so here we go. What? All right. Our power, if we're talking about statistical power, power defined as long-term probability of rejecting our null hypotheses given a particular effect size, alpha, and sample. Okay. So basically what this is think about our frequentist approach to most of the things that we're working on, right? The idea being that if I were to do this study again and again and again and again and again, pulling from the same population, having the same sample, going through the same procedures, how often would I detect this effect that I'm trying to detect? Okay? People kind of understand the concept of power. Again, it's a frequentist approach so that, again, over long-term probability, over replications, what's the percentage of replications that are going to identify this effect? So if I go through and I have a study that I think is adequately powered and I fail to find the effect that I'm detecting, does it mean that I've necessarily done anything wrong in the calculation of power? What do you think, Sam?
No.
Right? It just might mean that this might be one of those times where I missed detecting the effect that that I want to collect, right? And so when we're calculating power, when we're working with this, power most appropriate when we're using this to determine the expected power of a planned study before we collect the data, right? So before we collect the data, when we're putting this study together, we want to see how likely it is that I'm going to identify this effect that I want to detect. What's my likelihood of finding that, so I can start to use that to make some decisions on how I'm setting up my study. And again, determine the sample that I need to achieve adequate power prior to data collection, right? This is all part of something that we're doing before we've got the data. After we've got the data, we get into some problems here with the use of power and interpretation and things like that. So these should be things that you're thinking about before you start your thesis, before you start your dissertation, before you start running that project in your lab. Think about what are the parameters, what are the characteristics, what am I going to need to do in order to maximize the likelihood that I'm going to detect the effect that I'm interested in detecting. Okay? So, but what we'll find is this isn't an exact science. Okay, oftentimes when we're running our power analyses, and you'll run into this frustration when you're doing this on your own for your own research, a lot of the times it's not like what's the p-value, it's is my power of this study likely to be closer to 0.8 or 0.3, right? Do I have an 80% likelihood of identifying the effect that I want to, or a 30% likelihood of identifying the effect that I want to, okay? Any ideas on why this might be? We haven't talked about it yet, but what ends up happening is we want to at least get in a ballpark estimate that suggests that our data is going to be, we want to have a reasonable chance to detect the effect that we're looking for. Okay, power 0.8, fairly arbitrary. Okay, but this is typically what we'll see as the standard for acceptable power of the study. If we've got less than 0.8, unacceptable risk of type 2 error. Okay. What this is saying, again, Alex, I'm going to say you are going to say running your thesis, your dissertation, and you run your power analyses, and you see that your power is 0.4, which says you've got a 40% chance of detecting the effect that you're looking to detect. Are you going to be excited about that? Right? This is a lot of time, effort, life investment into this thing for something that's less than a coin flip, right? Oftentimes, that level of uncertainty is going to be unacceptable, right? 40% of the time you'll get it, but again, if we're thinking about anything less than 0.8, and again, depending on the study and what we're doing and what the potential outcomes is, oftentimes we'll say this is sort of underpowered study. But we can also have too much power, right? You can have power greater than 0.8, and this could mean, as Stephanie had mentioned, maybe this isn't a good use of resources. Maybe I've got a really powerful design where I'm doing a repeated measures assessment, running through and collecting physiological responses on people, and so I say, all right, I'm going to collect 100 people. And 20 people would be plenty fine, right? Again, wanting to know that before you invest time and resources, things along those lines. And then also overpowered studies, potential for unwarranted conclusions. Given what we've talked about to this point, any guesses on the #1 thing that contributes to a powerful study? Sample size, right? Sample size. And if I collect 1,000 people, right? What's going to happen is that's going to be an incredibly powerful study that I might start to pick up very, very small effect sizes as statistically significant, right? I might start to find that seemingly random variables in my study are coming up as statistically reliable, right? This is a straight up function of you having 1,000 people in your sample. But what can happen if people aren't being careful about their interpretations, they say, oh, this is a new focusing on, when really what they've got is perhaps a small, maybe it's real, but a trivially small effect that's only significant at p less than 0.001 because they've got 1 billion people in their sample, right? So wanting to think about these things and taking power, our hypotheses tests, our effect sizes all into play and starting to think about our approach to our studies. Okay. So want to give you a demonstration and thinking about what's actually going on with power. We can think about this in a couple of different ways. Take the example of stereotype threat, right? Social person, tell me what stereotype threat is. Or a clinical person.
So like, for example, if a woman in a STEM field operates under stereotype threat, it means that she's aware that people think she's less competent than other people, and then she reacts.
Exactly, right? So this internalization of this is, stereotype starts to influence performance, right? And so Aronson in '98 found poor performance on a math test among white males informed that Asian students generally perform better, right? So we've got a bunch of white non-Hispanic guys, we bring them in, and we have two groups. One group, we just give the math test to these guys. Other group, we give the math test, but we say, oh, hey, P.S., Asian students tend to perform much better on this than white students do, okay? And so what we do is we got groups of 20. The control group, these are the people just got the just got the test with normal instructions, scored 9.6 with standard deviation of 3.2. But our threat group, 20 individuals, a mean that's lower, consistent with stereotype threat, and a standard deviation of 3.03. So what we would do if we wanted to say we're interested in replicating these effects, right? And what I want to do is say, given a certain sample size and a certain alpha estimate, what's the likelihood of me replicating, finding this stereotype threat in using an independent sample test with groups of 20, okay? So if we're using these as our population parameters, let's see that these are perfectly representative of the population parameters, okay? What we would do is I would randomly select 20 observations from a population of scores having a mean of 9.46 or 9.64 and a standard deviation of 3.17, okay? So I've got this pool of scores, right? And the pool of scores has a mean of here, standard deviation of here, and I go through and I pull 20 individuals out of that, okay? And then I randomly select 20 observations from a population of scores having a mean of 6.58 and 3.03 as a standard deviation, okay? So I've got two pools, right? Two massive population pools, and I'm just randomly grabbing 20 scores out of this one, 20 scores out of this one, okay? Then what I would do is, based on my sample of 20 here, my sample of 20 here, calculate and record my t-statistic for the difference in means, okay? So how many studies have I run up to this point? Just one study, right? And then I do this again and again and again and again and again and again, okay? What I would do then is I would plot the frequency of my test statistics, right? So over 1,000 replications, randomly drawing 20 scores from my population with a mean of 9.64, and randomly drawing another 20 scores from my population of 6.58, running that test and doing that again and again and again and again and again. If I did that 1,000 times, okay, and plotted out the frequency of my t-statistics, okay, here my sampling distribution are the test statistics that I'm calculating from each one of these studies. People following me up to this point? Did I lose anybody? This is tricky. Okay, and this might be the distribution of my t-statistics over 1,000 replications, okay? What I would then do is I would find how many t-values that fell at or beyond 2.024. Where did I get that value? Why is this a relevant value? That's right. This is my critical T for 18 degree, or 38 degrees of freedom, right? So basically, what I'm doing with this distribution of t-scores, over 1,000 replications, what I want to do is I want to find how many of those tests were statistically reliable. How many of those test statistics fell at or above 2.024. And when I do, I find that 86% of the values, 86% of the replications that I ran produced a t statistic greater than 2.024. Okay? And so the area under this curve, or the number of replications, going to be about 0.86. So I would say in this case, my power to detect an effect using cell sizes of 20 for this is 0.86. Right? That's my power. Saying 86%, about 86% of the time, I'm going to find this effect in using cell sizes of 20. So, Lauren, what's going on here in this unshaded area? What happened here? There wasn't an effect, right? My test statistic fell below my threshold, right? Does that mean that there was no stereotype threat in this group in this set of tests? No. Why not? Could have existed, or it does exist?
It does.
It does exist. It's a thing, right? Like, it's out there in the universe, right? We know that because we're pulling from populations that we know are different, right? But sometimes when I just randomly draw 20 people from this group and 20 people from this group, sometimes I'm going to get samples of 20 that don't differ enough for me to claim a reliable effect, right? And this is here. And so what do we call this piece? Yes, type 2 error. This is our type 2 error. We've failed to reject the null hypotheses when there is something there, right? It's not that it's not there, we just missed it. We didn't have, just happen to be the samples that we drew didn't cut that threshold, right? But in a case like this, 86% of the time, we're gonna get this, we're gonna get the effect that we're looking for, okay? Any questions on thinking about power in terms of sort of this frequentist replication type of approach? Okay. All right. Other way to think about this, right? And probably maybe a little bit more complicated, but something that's going to be more, probably a more flexible way to think about this. Thinking about power in terms of overlapping distributions. Okay. What we have is we have a sampling distribution of the mean that we use when the null hypothesis is true, right? In this little figure here, this is our null hypothesis, our null distribution here under HL, okay? And our null hypothesis is that under the null, our expected mean is 80, okay? And so that's this distribution here. But we also have a sampling distribution of the mean when the null hypothesis is false, right? When the actual, when our sampling distribution doesn't have a mean of 80, our sampling distribution has a mean of 86, right? This is a different distribution. This is this distribution here, right? And so in this first sample, we've got a mean of 80. Second sampling distribution has a mean of 86. But what we do is these aren't completely independent distributions. There's a lot of overlap, right? Which one of these distributions are we looking at when we're running our hypothesis test? Okay. Yeah, and which one is that? Is it yeah, right? So this it's the null, right? So this is the distribution that we're expecting based on our null hypotheses. But H1 is actually the sample that we're pulling from, right? We're pulling from this, but we're testing against this, right? And so what ends up happening is we have overlapping distributions. And so what we have is our heavily shaded area in the tail of the null right here. This is our alpha level, right? This is past our critical value. Under the null hypotheses, this point right here, this is where, assuming that the null hypotheses were true, that this would be the region that we would be willing to say, all right, there's something else going on here, right? So if we just think about our null distribution, this is our alpha region, okay? But if we go through and we shade this area over here, right? Think about this. So this is the hypotheses that, or this is the distribution that we're assuming, okay? This is the actual hypotheses that, or the actual distribution that we're testing from. But sometimes, even if I'm drawing a statistic from this hypothesis, or from this distribution, this alternate distribution, if I get the average level of this alternate distribution, which is going to be right here, right? Am I going to reject the null? Alex, you're shaking your head. No, why?
Okay, wait, say it one more time.
So I've got two different distributions, right?
Mhm.
If this is the case, is there a difference in the population? Am I looking at a real effect in the population? What do you think, Alex? Does this suggest a real effect in the population? Yeah, it does. Why? Katie?
Doesn't that mean that the effect is one standard deviation, so the means are
Well,
standard deviation?
not necessarily. It just are these hypotheses, or are these distributions directly on top of one another?
No.
No, they're different. They're literally they're not the same, right? Suggesting that in the population there is a difference. They're different here, right? But they're kind of close, right? And they're overlapping, right? And so if I were to randomly draw a sample that fell directly at the mean of my alternate hypotheses here, right? The distribution, this is the one, this is real life, right? This is real life. This is what we're assuming under the null, right? But if I choose a score and have a mean that falls at the mean, or a sample that falls at the mean of my alternate distribution, why am I not going to reject the null hypotheses, Alex? Does the mean of this still exceed our critical value under the null? No, it doesn't, right? So even though there's a real difference, right? And think about this, remember when I had you guys do that problem where you were taking a look at scores in the 4th grade class and the 6th grade class, and so this is the distribution of reading abilities in the 4th graders and the 6th graders, as you go through and plot out the two different distributions? Same thing, right? So we've got, this is a student distribution of 4th graders, and this is distribution of the 6th graders, right? And some of those 6th graders are reading at levels that are kind of consistent with normative levels for 4th graders, right? And some of the 4th graders reading at levels that are normative for 6th graders. What we're trying to do is to figure out where these scores are relative to which distribution, right? And so in this situation, we've got a null distribution here, that's what we're assuming. And then we've got our actual distribution that we're pulling from, which is our alternate hypotheses here, right? Or our actual population distribution. And sometimes we're going to get scores in this distribution. So all of these, this is all reasonable values that we could reasonably come up with when we're pulling from that alternate distribution, right? But some portion of these are still falling within the body of our null distribution. And so if they're falling in the body of our null distribution, are we going to reject or fail to reject those? We're going to fail to reject, right? Because they're still, even though it's coming from a population with a completely different distribution, right? They're still falling within what we would expect to be typical, not atypical at least, of the null distribution. And so even though there is an effect there to be had, we're not going to claim an effect, And so what type of error have we made? Sam? Type 2 error, right? This is all this gray, this dark gray area here, this is all our type 2 error, right? These are all values that could be drawn from our actual population distribution that are still falling within the body of our assumed null, right? And so this dark gray area, or this light gray area here, these are all values that are sort of values that can happen within under our actual population distribution. They're just not big enough for us to claim a reliable difference because this is the cutoff under the null, right? So this is our type 1 error, or excuse me, our type 2 error, and this here, this is our power, okay? This is where these are, from this point in our alternate distribution to everything more extreme, these are all values that are gonna fall beyond what we would consider under the null to be atypical, assuming that the null hypotheses were true. And so that's going to be our power, right? This is our power estimate. So in this case, our power is going to be, is our power good or bad here? What do you think, Steph?
It's not great.
It's not great. How do we know it's not great?
Because there's so much overlap between the distributions that we would need a pretty large effect to be able to detect it.
Well, and in this case, right, we don't get to change any of this stuff, right? These are distributions that we get of a given size and a given effect, or of a given sample and a given effect size, right? And so here, our power is probably 0.4 or something like that, right? Where would we see this distribution shift if our power was 0.5? Yeah, right? If our mean lined up directly with our cut point on our null distribution for, if exactly half of this was gray and the other half wasn't, then that would be would be 50%, right? So we've got a whole lot more. As I randomly draw samples from this distribution, I'm more likely to draw something that fails to reject my null hypothesis than something that does actually reject the null hypothesis, right? What if, though, we do something like this, right? We say, now instead of, our reference population is still, our expected mean under the null is still 80, but now our population mean that we're actually pulling from is 90. What's happened to our power here? Take this one too, Seth.
Oh, it increased.
How do you know that?
Because technically I can't tell you, but you can see on the distribution that that area that the floor power is
Yeah,
larger.
it's less overlap, right?
Yeah.
And so we've got, if this is still our critical value, right? Because we're still, you know, we didn't change the sample size. What do we change in this scenario to that scenario? What changed? What's that? The mean, and what's that going to correspond to, Morgan?
Projecting the null.
Right. But if here we've got a difference between the mean of our population, the mean under the null of 6, and here in this scenario we've got a mean of our population versus the mean of the null of 10. What changed in these two? Yeah.
The difference of the effect size.
Perfect. Our effect size, right? Remember, our effect size is the actual effect in the population. Our effect size is the actual sort of relation or difference in the population. We've got a bigger effect size here, right? Now, we don't know what the standardized effect is, but we've gone from a population difference of 5 or 6 to a population difference of 10. And so what we've done is we've made that effect size bigger. And so all things being held equal, if I have the same number of people and the same methods and things like that, as my effect size increases, what's going to happen to my power? Power is going to increase, right? And so what we did in this, we're say looking at a small effect where we got a lot of overlap, and so our power is very low here. Here, our power is better, right? It's still not 0.8, it's still not where we'd like it to be, because everything falling, again, remember that this is the distribution that we're pulling from. This is just a reference distribution, right? This actually doesn't correspond to anything aside from what we're expecting under the null hypotheses. This is what that could be pulled from our actual population distribution that are still going to fall to the left of our critical value, right? And so if they're falling to the left of our critical value, are we going to reject or fail to reject? You think, Maureen? They're falling to the left of our critical value.
Sorry.
Fail to reject, right?
Yeah.
So these are all, because again, here's our marker, right? And this is the same marker, right? So we've selected this marker based on its position in the null distribution, but it's still hanging out in the same spot in our population distribution. And so anything falling to the left of this, we're still going to fail to reject, right? Even though we've got a big difference, these are just tests that we are not going to come up as becoming reliable. But all of this area out here, anything falling to the right of that are going to be samples that can be drawn from this distribution that are going to reject the null hypotheses, assuming the null, and we've got a much larger, our power's, I don't know what it is, but it's above 50 here, versus considerably below 50 over on here. People understand this idea of overlapping distributions and what's going on with this? Okay. And so again, the big thing here is we've got a difference in effect size. In this, we're looking for something that's corresponding to a relatively small effect. Here, we're looking at something that's a bigger effect. And so what we end up, if we're thinking about this in terms of overlapping distributions, more opportunities to randomly select a sample that's going to fall beyond the critical value under the null. Okay. Yeah?
Can you explain the difference, like what happens to type 1 and type 2 error across these figures?
Okay.
If that changes.
So don't worry about type 1 error. Type 1 error doesn't come into this. Why doesn't type 1 error fall into this?
Because they're not completely overlapping.
Exactly, perfect. And so why does that tell us that type 1 error isn't an issue? Can we make a type error here, Katie?
We can make a type 2 error, but we can't make a type 1 error because there is a difference in effect.
Absolutely, absolutely right. We can't make a type 1 error, right? There's no type 1 error to be made because they're different, right? Our type 1 error is saying that there's, claiming there's an effect when there's not. There's an effect, we can't make a type 1 error. And this is Cohen's argument about one of the problems with our whole approach to science to begin with is that there's always going to be some difference, right? These distributions will never be exactly on top of one another. So this preoccupation with type 1 error is kind of ridiculous because there's always going to be some problem, right? The worst thing we can do is claim an effect in the opposite direction of what it actually is, right? And so here, type 1 error doesn't even factor in because we can't make type 1 error here. All we can do is make type 2 errors, right? And our type 2 error is determined by the extent to which these our population distribution is falling to the left of whatever our critical value is under the null. Questions about this? This is kind of a heady thing to get your mind around, but we'll encourage you to go through, take a look at this because this is going to start to become just really important for some higher level stuff that we'll talk about later on. Yeah.
I almost changed my mind about asking.
No,
this,
ask me. It'll be an excellent question.
Okay, so this is why effect size affects power. So I'm assuming that sample size affects power because then the distribution, because when you have larger samples, there's more variance. So that would also change the distributions or the overlap. But I'm having trouble figuring out how it would look different.
Okay, no, that's a good, and so want to be careful, Sam and I discussed this. So larger samples doesn't decrease your population variance or your sample variance. Sample variance should be relatively equal because we have adjustments on your sample variance with smaller samples, right? But what does larger samples decrease?
Error.
Your error, right? Your standard error, right? And so let's say that this is, in this situation, we have a small effect, right? And so here our power's pretty poor, right? We're not excited about our power of this study. But let's say that this involves looking at groups of 10 and groups of 10. Okay. What would happen if we cranked that up to samples of 50? Would this difference change? No, because that's the population effect. What would change? Because that's going to give us a lot more power. How is going from a graph that would look here to a sample, if we're pulling samples of 50 as opposed to 10, what would change?
Critical value?
Critical value would change. Critical value would change, yeah. But what's the big thing that's going to happen?
Like the height of the graph, like how.
Not the height. The height's not going to change.
The power?
Power is going to increase, right? But what's going to happen graphically if we were to look at these? What happens to our sampling distribution as our sample size increases?
More normal? Don't they get taller and skinnier?
Not taller, skinnier, right? The variability decreases. My standard error decreases. Remember, your standard error is the standard deviation of your sampling distribution, right? If this is a sampling distribution of sample size 10, and I crank this up to sampling distribution of sample size 50, right? This isn't going to change because that's set. Like, that's just the population effect, right? What's going to happen is we're going to start bringing that sample in, that distribution in a lot more closely, right? So what you're going to end up with is, instead of this situation, you're going to end up with, right? It's still the same, right? I don't know whether they got these witch hat distributions here, right? But what's going to happen is your sampling distribution, your variability, your standard error is going to decrease, right? And so even though that's the same in both of these, right? What ends up happening is we just tighten up our precision, right? We have here, we've got a lot of room to vary around our population mean, right? We can get things going from really high to really low, right? But as our sample size starts to increase, that's our standard error shrinks way down, right? And so all of a sudden this, which was a reasonable value to find under our population mean in sample size 10, would be incredibly extreme to find under our with a sample of, say, 50, right? And so that's the difference here. We're assuming that we've got, say, the same size sample here and here. We're just assuming that we've increased the effect size. But if we increase the sample size, okay, and so can we have an impact on the population effect? No. I mean, we can do a better job of measuring it, right? So what ends up being the main factor in increasing the power of our tests? Sample size, right? And so what that does, that brings in those distributions so they're much more tightly clustered around the mean value than when we have larger samples that are much more variable. How you doing? High five. How was the conference?
We were meeting with the meeting recovery center.
Oh, okay.
It was good.
Nice. Well, this is fun, right? You like roll into a 2-hour car ride into a stat class, right?
5 hour.
Right. That's good. That's exciting for you. All right. Cool. Any people kind of got the hang of this, understand what's going on with this? Okay. Cool. So influences on our power, our effect size. Bigger effect sizes correspond to bigger power, all other things held equal, right? So again, here, same samples, right? If we're looking at something that's got a bigger effect, it's going to be easier to detect that effect, all things being held equal. Yeah?
We're still looking at the T's, right? The distribution of the T.
Yeah, yeah.
So that means the T's would like kind of converge more.
Well, I mean,
If you
think about this as just a general don't think about this in terms of T's, think about this in terms of sampling distribution of means, right? Just to keep it simple. But you could apply this to a distribution of a T statistic, yeah. So our effect size is going to increase, right? So if we're generally looking for things that have a larger effect, it's going to be easier to detect than if we're looking for things with a smaller effect. What are the types of effects that we're typically looking for in psychology? They're small or large? They're small, right? So it's sort of not much we can do about our effect sizes, right? I mean, there are, but that's a methodological issue, right? We can start to sort of increase the intensity of our interventions or of our manipulations to try and do that, or specific, grab groups that are very different to try and increase the magnitude of that effect. But the effect is what the effect is. Also influencing power are alpha levels. If we increase our alpha level, it's going to increase our power. What's the problem with that? Can we just set our alpha level to whatever the hell we feel like? Probably not. We're probably going to get in trouble, right? Like, oh, I'm going to set my alpha to 0.15. Probably going to get pushback from reviewers, right? So we can't do much with this in terms of our standards. Population variance is also going to impact our power. Variability in sampling distributions is associated with our variability in our sampling distribution is going to increase as our population variance increases. What do we call the variability of a sampling distribution? Eddie, what's the variability of our sampling distribution? Yes. Standard error, right? As our population variance goes up, our standard error is going to go up, all things being equal, right? But again, that's the smaller effect on our standard error. What's the bigger effect on our standard error? What's the biggest determinant of our standard error? Yeah.
Sample size.
Sample size, right? Sample size is going to drive down that standard error every time, right? And so the variability of our distribution of sample means is going to decrease as our sample size increases, right? So effect size, we can't do much about that, right? We can start to choose a study that maximizes our effect size, but then we can start to get into problems with generalizability and sort of whether or not we're demonstrating anything that's useful, right? If I say, hey, look, people who I shock a whole bunch in the lab get more upset than people who I let pet puppies, right? You're gonna use that as your magnitude of your effect for how much people like animals, right? Well, like, yeah, kind of maximize that effect, but that's not an effect that actually translates into anything in the real world, right? So oftentimes our effect sizes are what they are, right? Our alpha levels were constrained by convention in our science. Those are kind of what they are. Population variance, we can again get better measures. We can get more precise assessment instruments, and that's going to reduce our variability because we're going to, the variability that we're going to get presumably will be true variability and not adding measurement variance on top of it, right? But again, there's not much we can do about our population variability, and so our sample size, this is what's typically going on when we're making, when we're trying to increase our power. If we can do something here, we want to think about those things, but generally it's just a straight up function of how many people do we have in our study that's going to start inching up our power estimates. Questions about any of this? Okay, cool. Estimating our effect size. So what we need to calculate power, we need to know our effect sizes, we need to know our alpha level, and then we need to know how many people we're planning to get in a sample, right? So in order to calculate power, in order to run power analyses, what we need is some estimate of the effect size, right? And so this ends up being the question, how do we go through and get a reasonable estimate of our effect size? Candace, would you mind going and checking that out and seeing what's going on there? Just provide one peace of mind. Right? There's probably not anything we can do anything about, but if it's a bunch of yahoos running around with video cameras. Right? All right. number one place that we're going to go through and try and get our effect sizes for our studies is going to be existing research, okay? This is why it's so important to report your median standard deviations, other relevant statistics, because I can guarantee you what's going to happen is you're going to be planning your thesis or your dissertation or some other project, and you're like, okay, want to run a power analysis, how do I get an effect size, right? How do I get something that reasonably approximates the effect that I'm looking for, okay? Sometimes you'll say, oh, this best case scenario is there's a study that's used similar measures, similar methodology that you can pull from, but oftentimes there isn't. Or if there is, they haven't reported mean standard deviations, things along those lines, right? But in general, there's probably something out there, right? There's probably, unless you're incredibly innovative, someone's probably done something that's similar enough for you at least to try to start to get a bead on what type of effect you're looking for. And if there is, you need to track that down and you need to calculate that statistic, right? Because that effect size is going to serve as a basis for at least your approximation of is my power going to be closer to 0.3 or 0.8? Okay? This is what we need to be doing, okay? But sometimes there may be a case where there's just nothing out there. No one has ever done this before. No one has ever looked at the relation between these constructs before. No one has done anything that's even close to anything that's gone on before. And in this case, what you might want to do is think about how much of an effect would I need to see in order for this to be a meaningful result, right? Think about, so I'm interested, I've got an intervention that's going to improve people's scores on the GRE, right? But what I'm saying is that I need to see an increase on the GRE on average of 40 points. Otherwise, this really isn't going to be worth the time and money and effort to people, right? And so what I might do is if I say standard deviation of the GRE is 100, then I need to see an effect size of 40, right? And so what I might then do if there's because no one's ever looked at this before, no one's ever seen whether or not this is going to be an effective intervention. But what I might do is I might call my shot and I say, okay, in order for this to be effective, I need to get an effect size of at least 0.4. And so then what I do is I then use that as what I'm going to do is I'm going to power my study to adequately detect an effect of 0.4. And if I don't see it, then I don't know, maybe there's an effect there, or maybe it's just, if there is an effect, it must be it's likely a smaller effect than 0.4, and if it's smaller than 0.4, then it really doesn't matter because it's not worth the time and energy and effort that I'm putting into this, okay? So this, you're using previous research to go through and try and figure out what's going on. Here, what we've got is a situation where we're saying, kind of calling our shot, we're saying, I need to see an effect of at least this to make this worth it, and so I'm going to power my study to that, and then if I don't figure it out, it might be that I have an effect of this much or greater, and I just didn't find it, but it's not going to be promising in terms of sort of this being what I'm looking for. Last thing you should do, and only in the case where no other options are available, right? Using conventional cut points. You say, well, if I'm looking for a small effect, then I'm going to plug this in and power my study to a small effect, to detect a small effect. Or a medium effect, I'm going to power it to detect a medium effect, a large power to detect a large effect. Okay. Where do you think we see most of these three options? Which one is the most common one that comes into theses and dissertation proposals and things? This is where I will laugh at you, okay? Is because, like, no, you see this, and people like, well, and so like I'm assuming a large effect, and so I need 20 people in my sample. I will ask you, what makes you think that you're going to find looking at a large, like, is this just wishes and magic that you like think that this is a large effect, right? Because it's nice, right? If we're looking for large effects, it's going to mean the number of people we need to get in our sample is much smaller, right? But I would argue that it's not worth tricking yourself into thinking that, believing that you're going to find a large effect when you're actually looking at a small effect. and your study has next to 0 opportunities to detect whatever effect is down there. So what do we got going on down there, Candace?
So all the doors are locked, so I can't actually get into the auditorium.
Yeah.
But I've listened for a while. It sounds like there's some kind of like a cappella group.
That's what I think.
I was walking fast.
You guys want to take a break? Go push around some a cappella nerds?
Yeah, so I think they're just like have really powerful, strong voices, or there are thousands of them.
All right.
And yeah.
Like there's no drums.
Yeah, like, it's a cappella with some nice drum beat. Okay, so again, this is what we see a lot of times, but this is not what you should be doing ever, right? Basically, you're saying either one, both, or not either, both. One, no one has ever done anything that's even close enough to what I'm doing to even try and make an estimate of what the effect size is. And then two, I am completely agnostic in terms of the level of effect size that I would need to find in this study in order to make it worth my while. And so, on account of that, I'm just going to assume a large effect and power my analyses to there, right? Knowing what we know about psychology, if this is what we're going to do, where should we power our sample or our study? Small effects, right? On average, in general, we're looking at small effects. One, because we're looking at some fairly subtle stuff, and two, our measures are generally terrible, and there's just a lot of error and mess, right? If I'm looking at differences in height, that's a very precise estimate, right? But if I'm looking at differences in neuroticism will probably do so, or some other construct, right, that isn't well measured or only observed indirectly through your self-report scores, there's a lot of fuzz in there. And if you've got a lot of fuzz in there, that's going to reduce my effect size, right? And so this is why this starts to become problematic, right? Particularly if you're saying, even if you're trying to hedge it back, oh, I'm going to assume a medium effect. You probably shouldn't, unless you've got a good reason to assume a medium effect, right? So how, says I don't know, often translates into I haven't thought that far ahead. I said, like, I couldn't, I don't, you probably didn't try, okay? Basically what this does, though, is it requires you to know enough of your literature, be familiar with papers and studies that have tried to do something similar to what you've done, and then go through and comb through that data to try and figure out if you can gather something that looks kind of like an effect size that you can then use to try and power your study. Okay? And even if we do that, even if we're using our best approach, right, we've got a study, and it's one study that's gotten something that's kind of similar to what I'm going to do, and then I go through and I say, all right, this is my effect size. How am I still, why might I guess that I'm still likely screwing myself over and being overly optimistic in my estimate of power? Given how we go through and publish studies, what should we probably expect about any effect size that we pull out of the published literature? It's probably too high, right? And so that one study that you found that had the effect that you're looking for, it might be that many, many other people tried to do this and haven't found it because either the effect isn't there or it's just much smaller than this one study that found it and was able to publish. So even if you're doing pulling from here, there's still a strong possibility that you're going to end up with an underpowered study because your effect size estimate is probably going to be too big if that's all it's done. What's our one saving grace in our literature, our research, that kind of helps to lessen some of our concern with overestimating our effect sizes pulled from the literature? What's out there that's available that might be a better use or provide a better estimate than just picking one study? Meta-analyses, right? Okay, and this is the other thing too. So maybe there's not one study, maybe there's 3 studies, and one of them has a huge effect size and the other 2 are kind of small. What are you likely to be tempted to do when you're calculating your power analyses? Use the one that's super big, right? If you can, if there is a meta-analysis that you can go through and say, all right, I'm looking at evaluating the relationship between PTSD and perceived social support, right? Probably what I should do is see if there's a meta-analysis out there that's combined studies that have been published and not published and kind of aggregated things down to what a reasonable estimate of this effect is. Perfect, that's what I should probably use. Okay. So, again, big issue here is not letting you trick yourself, even for understandable reasons, into overestimating your effect size, because it might mean that you finish up with your thesis or dissertation data collection sooner, but it also means that that's likely to come at the cost of you putting in a semester, 2 semesters, 3 semesters of work, and not being able to say anything about your hypotheses because you haven't achieved significant, sufficient level of power to be able to detect what it is that you're trying to detect. Questions on any of this? All right, let's take a break, and we'll jump into some of the complexities of calculating power stuff. All right, folks. I'm going to go through and start talking about quickly going through calculation of power, just so you see how to go through and do this. But then I'm going to give you a computer program that's going to negate the need to do any of this by hand, but still want you to know how some of this stuff works. Main issue to think about, the big thing that makes calculation of power, or has up until recently difficult, is this non-centrality parameter. Okay. So if we think about our test statistic, our t-distribution, our test statistic distributed around 0, as long as our value, whatever value we have under the null, is the true mean of that distribution. Okay. So if there really is no effect in the population, if there really is no difference, if the population value is equal to whatever our estimate is under the null, then our test statistic, our t-tests, are distributed in a central t-distribution, the same one that we've gone through and worked on with our hypothesis test, right? But if the null hypothesis is false, right? If the actual population mean we're looking at is not equal to the population, or to the value that we specified under the null, then the distribution of our t-statistics that we're calculating is no longer centered around 0 because we're subtracting the wrong population mean. Okay? So if I say I've got a sample of individuals who go to Ivy League schools, right? And my hypothesis is that people who go to Ivy League schools are more intelligent than people who don't go to Ivy League schools, right? Or smarter than the general population, right? And so I sample 100 people who go to Ivy League schools, and I give them an IQ test. What's my value under the null hypothesis? What should I expect IQ to be if there's no difference between people who go to Ivy League schools and people who and the general population? 100, right? And if people who go to Ivy League schools really are not any more intelligent than the general population, right? Then the distribution of the t-statistics that I would calculate based on an infinite number of replications of that study is going to follow our central t-distribution, because we're going to be taking their mean, their average intelligence, and subtracting it from the population mean, which is actually the population mean of individuals going to Ivy League schools, and I'm going to get a nice t-distribution that is distributed exactly as what we would find in a table. But if it turns out that my null hypothesis is false, that people who go to Ivy League schools are actually systematically smarter or less intelligent, maybe, than the average person, then what ends up happening is this numerator is wrong, right? I'm not subtracting the appropriate null hypotheses, and so what ends up happening is I get a different distribution. In this case, the t-distribution isn't centered around 0. T-distribution is centered around some other point that we identify as delta. Delta is our non-centrality parameter, okay? And this shift from 0 over to delta, this is our degree of non-centrality with our delta, the value for delta representing our non-centrality parameter, okay? And so our issue of power then becomes a central distribution that's greater than a critical value of t under the null hypothesis, okay? So getting back to this idea of overlapping distributions, right? This is, what we're doing is we're comparing this non-central distribution, right, against values under the null distribution. People kind of see what this we're talking about. So we've still got this, and think about overlapping distributions. Still got this distribution, but instead what's happened is we've shifted it, right? We've shifted it over, and that degree of shift, the new place where that where our non-central t is distributed around delta, which is referred to as our non-centrality parameter. Okay, and already what we've talked about. What should that non-centrality parameter be related to? What do you think, Steph? When we shifted that distribution, what determined the degree to which those distributions were overlapping?
Difference.
Yeah, what causes that shift between the population parameter and the parameter under the null? Yeah, right. So absolutely, this is our effect size, right? And so we've got a big effect size. It's going to be way the hell over here. Smallest effect size, kind of overlapping, right? But because that t distribution, when the null hypothesis is false, is centered around our non-centrality parameter. Non-centrality parameter has a direct relation to your effect size. Okay, people. This is a kind of complicated thing, but people following me up to this point? Okay, so what we can do then is start to use this information to calculate the power of our different statistical tests that we've reviewed up to this point. So what we would do, and this is what we used to do, not anymore, but what we used to do is calculate power based on tables that assume a certain value of delta and a certain power of alpha. Okay, so for our single sample test, right, this is our one sample t-test, we need to find our effect size, which is our sample mean minus our reference population mean over standard deviation of our sample. Okay, do we have to worry about the standardizer with the single sample t-test? Angeline, you're shaking your head no. Why is that? Yeah, there's just one, right? We don't have any other options. This is the only one we have to work with, right? And so then once we calculate our effect size, we then take that effect size and multiply the square root of our sample size, which gives us our non-centrality parameter. So let's say we have a question. We want to see, do people seeking treatment for psychological problems have higher IQs, right? People have heard about this before. Like, oh, you're a crazy genius, right? People who struggle with anxiety, depression, these are people, and psychotic disorders, they're actually smarter than the rest of us, and sort of this is what's going on, right? And so maybe we want to see this. And so what we do is we've got, and again, this is a previous study, right? So we've got one study that's looked at this, right? And so we say, okay, that study had a mean of 105, reference value of 100, 25 people, and a standard deviation of 15. Okay? And what we want to do is we want to go through and calculate, if this was a study that we were going to run, what would our power be, assuming these parameters? Okay? So what we would do first, calculate our effect size. This is easy, you guys have been doing this. 105 minus 100 over our standard deviation is 15. Gives us an effect size of what? 0.33, right? So we take 0.33, multiply that by the square root of our sample size, which is 25. And what do we get, Alex, off of that? 1.65, okay? So people have this power table that I handed to you last week. Anybody heard that? If you have it, or look at someone who does. Who has that? What's that? You got yours? Morgan, do you have that with you?
I do.
You don't, Katie doesn't have it. Stephanie, you have yours?
Yes, I do.
Okay. Yeah, no, I'm not. Katie, you can go back through, take a look at Stephanie's power table here.
Oh, okay.
Yeah.
Then yes, I'm glad I could.
All right. Alex, you have yours?
It's summer. I'm just really unorganized. It's a problem.
All right. Morgan, did you find it?
I have it pulled up.
What you have pulled up? Okay, perfect. Okay, cool. So, Alex, you said our non-centrality parameter is equal to 1.65, right? So what we would do is then we go through on our power table, and in the left-hand column here, you'll see delta. We would go down and we would find something that's close to 1.65, right? So we've got an entry for 1.6, we've got an entry for 1.7, right? And so 1.65 directly between those two. So we would walk over for our alpha on our two-tailed test is 0.05. And so these values in the body of the table give us our power estimates. Okay? So Sam, assuming that our non-centrality parameter delta is 1.65, so falling right in between 1.6, 1.7, what's our power? What's our expected power for this test? About 0.38, okay? And if we run this, power is about 0.38. And if we make a literal interpretation, assuming that the null hypothesis is false, right? Assuming that people who get treatments for psychological difficulties do have a different, are smarter than people who, than the general population. Assuming the null hypothesis is false, our effect is expected to reach statistical significance 38% of the time, given a sample of 25 and a population effect of 0.33. Are we happy about this? No, right? Basically, this is saying about a little under 2/3 of the time we're not going to find this effect, even though it is an effect to be found, right? Why is our power so poor in this study? Yeah, we have a small sample size. And so maybe what we might want to do, like, well, boy, that's a kind of miserable, I don't like, this isn't worth me doing, bringing in a bunch of people who are experiencing psychological difficulties, running through an IQ test, if I would plan to get 25 for only about a 1/3 chance of actually detecting this effect that I'm expecting to be out in the population, right? And so what I could do is I could go through and say, all right, what's the sample that I need to achieve power of 0.80, right? This is pretty easy to get. You just take your sample size, your expected sample is, or your required sample is equal to your delta over your effect size squared. Where did I get this? Where did I get this equation from? Yeah, it's just, yeah, it just on account of algebra, right? We just restructured this, right, and got this, and so we're just solving for n instead of delta here, right? And so here, I'm going to take 2.8 over 0.33. Where did I get 2.8? Perfect, right? Angelin's found this. If we go down through and we take a look at our column for alpha 0.05, if we go down, what we need to get in terms of a power of 0.80 corresponds to delta of 0.28, okay? And so when we're running our power analyses, if we're trying to power things to 0.80, is this value going to change? No, it's going to be the same always, right? And so we just take 2.80 over, where did we get 0.33? Our effect size, and square that, okay? And so someone do that for me. Take 0.2, or take 2.80 over 0.33 and square that. What is it, 70?
72.
72, right? So, assuming that we have an effect size of 0.33, with a single sample test, we would need to have a sample of about 72 in order to achieve adequate power. Okay? So you can start to see how we've gone through, we've taken an effect size that we've pulled from the literature, and then run this through our power analyses to say, if this, and this is a big assumption, but it's assuming that this is a perfect representation of the population effect, how many people would I need in my sample in order to detect this effect 80% of the time, right? And in this case, it's 72, right? So you can see where the fuzz comes into play, because this is probably not a perfect estimate of the population effect, right? Our population effect is gonna, our estimate of population effect isn't gonna jump around. Our estimate of the population effect is gonna jump around, right? But doing our best guess, we can say about 72 people in my sample is gonna get me close, right? And so then I can start making determinations on how many people I want to plan to collect in order to adequately power this study. Questions on this? Okay. So I mean, the math is actually pretty simple once we have the tabled values. These are really difficult, right? And this is one of the things that's made doing running power analyses incredibly difficult, especially as we start to get into more and more complex analyses. But for our means-based analyses, pretty straightforward at this point. We can also take a look at our independent sample t-test. And here we're assuming that we've got equal samples. What we're going to do, detect differences, looking at power to detect differences in sample means. Our effect size is just our D that we've run before. So we've got mean 1 minus mean 2 over standard deviation estimate. And then our delta, our non-centrality parameter, is just our effect size multiplied by our sample size for the number of cases in either one of our samples. And again, we're assuming equal n. So it's our cell sample size, not our total sample size. Make sure that you're clear on that, divided by 2. So we want to know what the difference is. We're running a study, and we want to know what the difference is between treatment 1 and treatment 2, right? Because we're going to rerun this. We're going to do some, maybe we're going to run this in a different population. And so we look through the existing research, and we find some mean standard deviations here, right? And so we say, all right, what I'm going to do is, assuming that the average difference between an outcome between treatment 1 and treatment 2 is 5 points, with a standard deviation of 10. What's our power going to be if we run 25 people per group? Okay. People see the setup here? All right. And so what we do, calculation of our effect size is easy, right? That's just 5 over our standard deviation estimate, and it's however we've decided to operationalize standard deviation for this. So we get an effect size of 0.5, take 0.5, multiply that by 0.25 over 2, take the square root of that, okay? Someone tell me what I get in terms of my my non-centrality parameter. What's delta in this example? 1.77, okay? And so if I go to my power table and go to 1.77 and take a look, see what my power, if this is a true representation of the population effect, and I go down through and I decide to collect 2 samples of cell size equal 25, okay, what's my power that I'm looking at?
About 0.44.
What's that?
About 0.44.
Yeah, about 0.44. Yeah, around there, right? I would put it at 0.33, probably not at 0.44. It's going to be under that because our non-centrality probably isn't right, so maybe you want to tone it down just a skosh. But I might guess that my power is going to be about 0.343 here. So again, assuming that the null hypothesis is false, assuming that there is a difference between these treatments, my effect is expected to reach statistical significance about 43% of the time, given a sample of 25 people per group and effect size of 50. Are we excited about this? No, we're kind of bummed, right? And I mean, for a group-based analysis, 25 people, that's not, I mean, for a treatment study, I mean, we're taking people through a whole like I mean, that's not, I mean, it's statistically small, but I mean, it's not an unreasonable number of people, particularly if you're looking at taking a group of people through group 1 and group 2, right? But still, and our effect size is about 0.5, right? I mean, that's medium, right? It's not a small effect. But even here, right, I'm still only achieving a power of 0.43. More times than not, I'm not going to detect this effect, even though there's an effect to be had. And again, I can go through, rearrange this formula to determine, okay, assuming that this is a reasonable estimate of the population effect, how many people would I need in each cell of my study in order to achieve an adequately powered test? Just taking 2 times delta that we would need over our effect size and square that. Again, in this situation, 2 over 2.8, because that's delta associated with power equal 0.80. Over our effect size, 0.5, squaring that, and what do I get? How many people would I need to have in each cell in order to achieve adequate power for this study? 63, right? Boy, right, you can see why people don't like running power analyses, right? Because basically what you're doing is I have to have a treatment study with 2 people, or excuse me, with 63 people, over 60 people per cell in order to get an adequate test of this difference in treatment effects of 0.5, right? And so if you're thinking about like clinical people, right, we often find that treatment A and treatment B, there's no difference between treatment A and treatment B, particularly if they're active treatments, right? Should start to think about, this should give you an idea why, probably what drives some of that. And what we often say is like, oh, all treatments are equal, right? Well, just because we don't detect a reliable difference doesn't mean they're equal. It just says we don't have enough power or enough evidence to say that they're different, right? But I mean, this is a pretty big treatment study. If I've got over 60 people in each treatment group that I'm then comparing, and particularly if I've got an active treatment, right? We can start to see how, like, if we're being realistic about our likelihood of detecting a reliable effect, even if the null hypothesis is false, we start to need pretty large samples in order to be able to do this reliably. Okay. So this is a situation where we've got equal samples, but what if we don't have equal samples, right? What does that do to our power if we have unequal samples? If we have unequal samples, what we need to do is we need to calculate a harmonic average sample size in order to adjust for these unequal samples. If we're calculating our harmonic mean sample size here, we've got 2 times number of people in cell 1 times number of people in cell 2 over n plus 1 plus n plus 2. This gives us our harmonic average sample size that will then plug into our power analyses. Okay. So going back to Aronson's stereotype threat, let's see, we have a mean of 9.64 with 18 in the control and a mean of 6.58 in our threat condition with 12 individuals. And what we've done is we've pooled our standard deviation, got a pooled standard deviation 3.1. We go through, calculate our effect size, that's easy, right? And we go through, we get a pretty big effect here, effect of 0.99. But then what we need to do is we need to calculate a harmonic average sample size by taking 2 times sample 1 times sample 2 over 18 plus 12, okay, which gives us a harmonic average sample size of 14.4. So then we take that sample size, plug that down into our equation to get our non-centrality parameter. So we've got our effect size, our harmonic average sample size over 2, and what do I get in terms of my non-centrality parameter in this test of, and this would be assuming I'm apparently planning to collect 18 people here and 12 people here. I'm not sure why I would plan to do that, but let's say that I did. What would be my non-centrality parameter? What is it, Alex?
2.7.
2.67, right? Okay. And if I do that here, it's not too bad. I get a power of 0.75 still, not that 0.8 level, but closer, right? So assuming the null hypothesis is false, the statistical test is expected to reach statistical significance 75% of the time, given samples of n equals 18 and n equals 12, assuming a population effect of 0.99. So so this is kind of weird. Like, I'm not sure why I would run an experimental study, and I would plan to have a sample size of 18 and 12 respectively. When might I run into a situation where I might expect to have different sample sizes? What do you think, Sam?
When you don't have enough, like, I guess the populations of different sizes, so it's not like equally available.
Right. If I know based on my research, right, let's say I'm doing something, one of Carolyn's students, right, and you know that it's going to be more difficult to get someone with non-suicidal self-injury than people who do have suicidal self-injury, who don't have it. And so this is going to be a smaller group, right? And so if I only get 15 people in this sample, I don't want to necessarily restrict myself to getting 15 controls if I can get more controls, right? But wanting to say, I'm expecting I'll probably end up getting twice as many controlled people than I'll be able to capture whoever my target population is or something like that, right? And so if you're looking at and know ahead of time that you're probably not going to be able to get the same number of this group versus that group, you can start to kind of plan out and say, all right, this is the ratio that I'm probably looking at with this. Okay. Notice this, okay? My effective sample size in here is 28.8. Where did I get that from? Why am I saying my effective sample size 28? Yeah, right. If I take my harmonic average mean sample, or my harmonic mean sample size, and multiply that by 2, basically I'm working with a sample size of 28.8 when I actually have 30 people in my sample, right? So what does this suggest happens when we start to get unequal sample sizes? What does unequal samples do to my power? It decreases it, right? And so this is something that you want to be thinking about in terms of going through when you're calculating your effect size. Noting that, again, if we were running perfect research and best case scenario all the time, our data would always be normal, our sample sizes would always be large, and we'd always have equal samples, right? That doesn't happen, but recognizing that if we start not doing that, there are real consequences in terms of our statistical inference and our ability to detect stuff. Okay, questions here? All right. What about then, if we want to go through and take a look at our paired sample T? Paired samples T gets a little bit different, okay? What we need to do with our paired sample test is we need to start to account for our relations between our measurements, okay? So what we have, when we're calculating power, we're going to calculate a very specific sample size for calculating power of an effect. Now, we talked about a lot of different options for our paired samples in terms of what types of effect sizes that we can calculate. When we're trying to calculate power for a paired test, we're locked into this one specific type. So we've got difference in time 1, time 2, right? Over what we're going to do is our variance estimate here is going to be our standard deviation. And then we're going to take a standard deviation and multiply that by the square root of 2 times 1 minus the correlation between time 1 and time 2. Remember, if you think back to our D-paired, right, you'll see something similar going on in terms of a correction. What this is doing is it's correcting for, or it's making an adjustment for the relationship between my repeated measures, okay? And this is important is because this is where we get the added power from our paired sample tests. So let's say we revise our stereotype threat example, okay? So we say instead of having a control group and a threat group separately, let's say we just collapse this, turn this into a one sample test, and we first have people come in and take an exam under no just straight instruction back, here's an exam to take the exam. And then we bring the same people in and we say, all right, here's another thing I want you to do, except note that Asian students do a lot better on this than you all will, right? And so what we end up with here is the first time people take this exam, they get a mean of 9.64, and they have, the second go around, they have a test reduction 7.55, right? But we're using the same sample of 30 across both assessments. But what we know is that if we pool, for the purposes of this example, if we take the variance at time 1 and we take the variance at time 2, create a pooled estimate of that, and then grab the standard deviation, we get 3.10. And we know that the test-retest correlation, or test-retest reliability across multiple assessments of this exam is 0.92. Okay, so we could go through, or if this is the study that we're basing on, we see that the correlation between scores at time 1 and time 2 are still 0.92. Okay, so that's the correlation between our assessments. What we would do is go through, we calculate our variance estimate here, we take our pooled standard deviation, and we multiply that by 2 times 1 minus our correlation between our repeated measures. Okay. If we do that, we get a value of 1.24. So we take time 1 minus time 2 over 1.24, gives us a what is our effect size here? 1.69. What do we think about that effect size? That's pretty massive, right? What would we get if we were to just calculate our effect size based on our pooled standard deviation? What effect size do we get if we were to just calculate this as something that we might report for our observed effect in this paired sample test? What did you get, Katie? 0.67. 0.67, all right. So we're talking about a difference between 0.67 and 1.69. This is why I don't want you reporting this as your effect size, because it makes it seem like you've got a really, really, really massive effect, when in fact, that's probably not a reasonable interpretation or a reasonable estimate for that effect. Now, for calculating power, you do need to use this for calculating power, but in terms of just an effect size that you would throw out there, not appropriate, right? Because it makes it seem like this is your big 1.7 standard deviations change, right? Which that actually isn't true. It's not 1.7 standard deviation change, it's a little over half standard deviation change, right? But this can be a misleading effect size. But for the purposes of calculating power, important, so we take our power effect size here that we've calculated, 1.69 times the square root of 30. Why are we multiplying this by the square root of 30? It's a sample size, but why aren't we taking the sample size, taking this by the sample size over 2? This is a single sample, right? Again, and I can't emphasize this enough in understanding with our paired sample. Our paired sample is just a single sample test of the difference scores, right? So everything we're doing is just the same thing as we would do with the single sample test. It's just our metric is the difference scores, right? So we use the same in the calculation of our power, use the same formula as we would for our single sample test, except that we're just calculating our effect size a little bit differently to control for correlation at time 1 and time 2. And so what do we get is in terms of our, what do we get in terms of delta? What do we get? 9.26. Where's 9.26 on your table?
It's not.
So what we've got, right, is we've way overpowered this study. We didn't need to get anywhere close to 30 people in a sample, right? We actually, if we go through and calculate the number of people who we would actually need to adequately power this test, assuming a mean at time 1 of 9.64, mean at time 2 of 7.55, pooled standard deviation of 3.10, and a test retest of 0.92, or a correlation between our measures of 0.92, we need 3 people. 3 people. Like 3 people will get you a reliable effect 80% of the time, right? How does that compare to what we did here? Right? Same kind of situation, right? But here we had 30 people and we were still slightly underpowered. Here we got 30 people and we're through the roof in terms on power. What happened? We used a paired sample, right? And this is what's going on with our paired sample. Our repeated measures go through and will consistently require smaller samples than will your independent sample tests, okay? Far greater sample, or far greater power with smaller differences and smaller samples than you would with a between subjects design. Again, what we're doing is we're calculating for the calculation of our power, right? We're calculating our effect size, adjusting for the correlation between our repeated measures, okay? What ends up happening is our repeated measures reduce our error variability. We systematically partial out individual differences. Subject level differences, like the differences across people in our study, we section those off, and so all we're looking at is the change across people. So it doesn't matter where you start out, as long as everybody's changing kind of the same, what we do is we partial out that individual difference, results in far less noise, okay? And our correction to our variance estimate here, our variability estimate, is a direct function of the correlation between our repeated measures, okay? Our effect size and our power start to increase dramatically as that correlation increases. As that correlation becomes increasingly close to 1, our effect size, our power goes through the roof. As this correlation between time 1 and time 2 decreases, basically what it does is it reduces us down to an independent sample test when there's no correlation between our repeated measure at time 1 and time 2. Okay? So this is why, if you're working with something, if you're taking a look at people's scores across repeated measures, and you know that those repeated measures are going to be very, very strongly correlated, you can anticipate having an incredibly powerful test, even with relatively few people based on this. Okay? So if we go through, and I were to calculate let's say, so in that last example, we had a correlation of 0.92. If I were to go through and run the same analyses, power analyses with assuming the correlation of 0.5, right? So we've got 3.10 times the square root of 2 times 1 minus 0.50. Okay. You're going to give me, well, what's this going to be? 0.5, I'm going to multiply 0.5 by 2. 1 and take the square root of 1. Yeah. Right. And so here, my effect size is going to be D equals 9.64 minus 7.55 over 3.10, you give me an effect size of 0.674, okay? So even though I've got the same, I'm working with the same difference between my assessments, right? This didn't change, right? But this correction I made to my denominator changed quite a bit, right? And so this is still a strong correlation between your two measures, right? A correlation of 0.5 is consistent with a large effect, but going from something that's close to collinear at 0.92 down to 0.5, we jump down from our functional effect size that we're using to calculate power, going from 1.69 to 0.674, right? And so recognizing that the power of your repeated measures designs directly related to the extent to which those two assessments are correlated with one another. Okay? As they start to decrease in this magnitude of their correlation, that your power starts to decrease down and becomes smaller and smaller to the point where once you hit no correlation, if your scores at time 1 are orthogonal to your scores at time 2, you're basically running an independent sample test at that point in time. Yes?
If you calculate where you only need 3 participants, what's the happy medium for reviewers as far as like how many people they expect?
It's sort of up to you. I mean, like if you collect a reasonable sample size, and then it's going to be overpowered, right? That's fine, whatever, I guess, right? Yeah, if you're trying to publish something with the sample size is 3 based on a power analysis, it says you only need 3 people. Be happy, and then just collect more people than sort of whatever you can that seems reasonable and convenient. But just know for that specific test that you'll probably be pretty good, right? But this is the other thing too that happens, right? Do we usually run studies where we have one hypothesis test that we're going to run? No, we probably have a number of different outcomes, right? So what do we power our study as a whole for? Power towards our smallest effect, right? Within reason, right? Now, Adam ran a study where 2 of his hypotheses, 120-ish people would have gotten in reasonable power, and then for his other thing, he needed like 500. So like, well, we're going to get 150, you know, or plan for maybe 150, and then recognize that this other hypothesis is aspirational, right? we obviously aren't going to collect 600 people. Our 3 hypotheses, 2 looks like an estimate. It says power suggested we need, 120. We're going to collect 150. Expect these 2 tests to be reasonably powered and these ones to be underpowered. But at least we know going into it that we're probably it's going to be unlikely that we're going to actually detect this because of stuff that's going on, right? So does that mean that we shouldn't do those analyses? No, right? Because even if we don't find a reliable effect, what can we do? Yeah, calculate an effect size, right? And if the effect size I get in my data looks like it's about the same as effect sizes that I pulled from to try and calculate my power, I can at least say, well, we knew that this test was going to be underpowered, but even though we can't claim a reliable effect, we're seeing effect sizes that are consistent with what's been found in the previous literature, which starts to suggest that there's maybe nothing there. Right?
I have a question for the slide back.
Yeah.
For the equation for delta, what happens if you have a participant drop out after testing? So you actually have different sample sizes, but you just exclude the data for that participant?
Yep. Where's that? You gotta have, like, if they're gone second round, they're out because we can't calculate a different score there. All right. So all of this is to say, repeated measures designed in any situation where this is remotely possible. Sometimes it's not. Sometimes testing effects, sometimes things like that carry over, make it impossible to use the same people. But if you can, if it's possible at all to incorporate a repeated measures design, do so, because it's just going to make your life a whole lot easier, at least in terms of collecting data. Calculations with G-power, I'm not going to, we won't do this here just because I want to get through some other stuff first, but here's G-power, right? This is a lovely little free to download program. I've got, I'll post up a screencast video that just basically demonstrates where to plug things into G-power, how to get stuff from there, and this is all pretty straightforward. So I'll let you go through, pick up that video, and it's just me walking through the examples that we, on that last slide, and how we would go about calculating power using the program we set by hand, okay? All right. All right, our write-up, right? This is something you want to go through. This is pretty easy, straightforward, right? Effect size of 0.45 expected based on the existing data from Jones and colleagues. Power analysis using these data indicate a sample of 32 individuals per group would be required to achieve adequate power, right? This is just, so the biggest thing here is probably this first piece, figuring out where to get an estimate effect, what study to use, and sort of how to sort of couch, is this a reasonable estimate for what I'm trying to do, right? Your study will likely vary in important ways from stuff that's out there already. And so again, one of the things you might want to start thinking about, so are there things about my study that are more likely to increase or decrease my observed effect, right? If there are multiple studies out there, maybe you want to calculate a power estimate for what's going on at the low end, what's going on at the high end, right? Assuming that I get something that's sort of at the top end of effect sizes that have been reasonably published, looking like I'm going to need this many people. If I'm more towards the low end, it's going to be down here. And then all I would ask is that you move forward with sort of clear eyes and recognizing that what you're doing, the choices that you're making here, they're going to change your numbers, but trying to do something that at least realistically reflects what's likely to happen in real life, right? Not just assuming that you're going to be detecting large effect sizes in optimal conditions, right? That's not to say every thesis or dissertation that comes through has to be adequately powered. They're often not, but I would prefer you coming in and saying, look, this is what we're going to do. I think this study is worth pursuing, even though I know it's going to have some problems with power here. This is what we can expect based on sort of be full information before you jump in, as opposed to thinking that you've got something that you don't and then being sad on the back end about it. Okay. Questions about any of this? Yes?
What's that picture about?
What?
Whoa. Oh, wait.
Who knows what that picture is from?
Oh, this is so sad. No one?
Is that in a commercial recently?
You saw that in a commercial?
Yeah, it's on a commercial.
Really?
Yeah, I can't remember what it's for though.
Interesting.
Is it like
It's He-Man.
Oh,
He-Man? Masters of the Universe? Okay. You need to go through and watch some
Like, I knew
He-Man.
who it was, but I had no idea like what he's all about.
What's that?
I don't know his psyche.
He-Man's about running around in shorts and stuff.
That's an understatement.
All right. So,
That was very.
ruined my,
That was really
who is that? Nice. All right, conceptual interpretations, all right? What happens if we fail, or if we fail to reject the null hypothesis in adequately powered study, right? So we go through, we do our due diligence, we say this is how many people we need to have an adequately powered study. We collect those individuals and we still fail to reject the null hypothesis. Number of different things you could be having. One, we have an error in our power calculations. We assumed we were looking at a large effect, but we weren't. We were looking at a small effect. or we pulled an effect size out of the existing research that wildly overestimates the effect that we're actually trying to detect. And so we might have just screwed up our power analysis and been way off base. Two, our effect size is smaller than we had anticipated, right? So even if we did get a good study that should get something reasonable, maybe something about our study is attenuated that effect that we're looking for, right? And so even though this sample would be adequately powered to detect an effect of this size, we weren't actually looking at an effect of this size, we were looking at an effect of this size, and so we kind of missed it there. Or we're just a simple victim of type 2 error, right? Again, in this situation, this is not adequately powered, right? We've got power of less than 0.50. This is looking like power of 0.45 or sort of 3.5, something like that. It's not saying that the effect isn't there. We're just hanging out over here in this area, right, where we missed out on some stuff. So how do we determine which one of these is right? We don't, right? And this is the frustrating thing, right? Like, did I miss an effect just because it's just not there? Am I chasing shadows, or did I not have a sufficiently powered test? Was there something that went wacky with my study? This is sort of the soul searching that needs to go on after you've run your analyses, and then try and be realistic in saying what's going on here. Because if I've made a mistake or underestimated power or something along those lines, then that's something I can fix. I can change my methods, I can collect a bigger sample size, and continue to pursue this research question as long as I think it's something really there. But sometimes stuff's just not there, right? And you see this sometimes. People get hyper-focused on one study that's found this one thing, and then I spend 10 studies trying to find this one thing, and it never shows up. You spent 10 studies trying to find that one thing and it hasn't shown up across the, you might want to presume that maybe that's not a thing that's worth chasing down. You see people sort of get fixated on a certain program of research and continue to beat a dead horse, even though every study that comes out is just not there, but continuing to claim that something is there. At some point you gotta let it go and be like, I don't know, it's either not there, or it's the effect is at a level that's so small that we can't reasonably detect it in reasonable studies. And so at some point, even if we all have our pet theories and hypotheses, sometimes we gotta let that go and recognize that that's maybe not something worth pursuing, right? But this all requires you to have a reasonable knowledge of your literature, what's been going on, and also understanding how methodology starts to impact whether or not we're finding things or not finding things, okay? Do a critical assessment of your study, the literature, and then just make a decision on where to move from there. All right. What have we got? I've got a Wilkinson quote in one way. Okay, yeah. Don't select your power or your effect sizes to justify a sample, right? Like, I only want to collect 20 people per cell, and so I'm just going to hunt around and find an effect size that will give me, that will tell me all I need to have is 20 people in each cell, right? I mean, you can do that, but you're not going to do yourself any favors in terms of reasonably putting together a study that's going to identify the effect that you want to detect. Okay, I want to go through quickly some thoughts on observed power. This Honig and Hasey paper is a good paper. Make sure that you go through and read this. But recognizing that power analyses are used primarily to determine plan for a future study, right? We do these before we've collected data to go through and determine how many people do I need to reasonably detect this effect that I'm expecting to be out there in the universe. Using power to explain observed data, strongly discouraged, okay? This would be after I've collected the data, after I've run the study. Now I want to run a power analysis on my study to see whether or not I have an adequately powered study or not, okay? The problem is, even though SPSS will give you estimates of observed power, right? And basically what it's doing is it's taking the sample size that you've observed and, or excuse me, the effect that you've observed and comparing that with the sample size that you collected, and then it's telling you the power of your study based on the parameters that you've already collected. And the idea is that, and the temptation is to try and infer something from that power analysis or that of that observed power to tell us something about the null hypothesis, right? The idea is that, boy, I ran through and I looked at observed power, and I failed to reject the null hypothesis, even though I have high power in this study that I've collected, which means that probably the null hypothesis is true, right? Because in this reasoning, my observed power is high, yet I failed to reject the null hypothesis, which suggests to me that actually the null hypothesis is true, right? Or conversely, say, well, I failed to reject the null hypothesis, but my power is low, which then therefore suggests that, you know, this is what's going on, is just I have low power, right? The problem is that our observed power is always a direct function of the p-value, okay? These hold a direct relationship with one another, and so what ends up happening in any study that I conduct that fails to reject the null hypothesis, what is my observed power going to be? It's going to be low, right? I can't, like, it's physically impossible to have a study where you fail to reject the null hypothesis that's going to give you high power. That just doesn't happen because observed power is a direct function of your p-value. So any study that you get where you fail to reject the null hypothesis is going to tell you you have low power, right? And so what ends up happening, so this idea that, oh, I'm going to get a study where my observed power is high and I've failed to reject the null hypothesis, that's not a thing, right? It just doesn't happen, right? And so any test that you run observed power on, you're going to find that you're underpowered. This really doesn't tell you about anything other than the fact that you already know that you weren't able to reject the null hypothesis. Okay? Only again, Hasey talk about, because observed power is completely determined by your p-value, calculation of observed power adds nothing to your interpretation at all, right? Again, this is one of these things that you can ask for it, it'll give it to you, it just doesn't do anything for you. And what ends up happening is people misuse sort of this interpretation. Also thinking about the calculation of parameter estimates that fall outside of your confidence intervals, right? The temptation being like, well, I've calculated my confidence interval, right? My confidence interval says values within my confidence interval are values that are not refuted by the data. Reasonable interpretation of this, right, is that I can go through and I can say, if I take a look at my confidence interval, and my confidence interval is fairly narrow, and it's tightly surrounded around that zero value, that's reasonable evidence that probably we never accept the null, but it's pretty good evidence that whatever effect is there, at least based on these data, it's pretty close to zero, right? If we've got a small, tight confidence interval around that null value. On the other hand, if my non-refuted values range widely around the null, I want to be very, very careful about concluding that there is no effect in these data. We would never do that anyway, but even implying that there was a near null effect, if my confidence interval goes from -20 to 20, that doesn't tell me a whole lot, right? I don't know. So the effect could be anywhere from very pretty big negative or very big positive. If my confidence interval is too huge to be useful for much, right? On the contrary, if my confidence interval is quite narrow, right, it's from -0.15 to +1.1, right? That's suggesting a very tight estimate of plausible values, all that are hovering right around zero. This starts to give me a better sense for, yeah, I probably got something that's pretty, if not near zero, at least pretty small, right? So again, using confidence intervals to start to infer something about the state of affairs in the universe. But once we've calculated that confidence interval, calculated observed power doesn't do much, right? And Honig and Hazy talk about this. Like, okay, well, based on the data that I've collected, these seem like reasonable values for the population parameter, right? But what if they're not? I'm going to calculate power of the study for an estimate that falls outside of my confidence interval, right? Why is that problematic? I don't know. Why don't we run a study to see how happy people could be if they could fly around the room? We could do that. People can't fly around the room, so it doesn't seem super. Like here's the range of values that seem reasonable for the population based on my data, right? But now I'm going to go run a power analysis. Like, well, what if it wasn't, right? Well, these are the estimates that are reasonable. What if we powered this next study to a value that's not reasonable, right? It's not a useful thing to do. Again, it's wishful thinking and oftentimes motivated by sort of what you were going to do anyway, right? If you're going to do it anyway, just do what you're going to do, right? Don't try and bring power into it and bastardize that for your own purposes, right? Just be like, hey, this is what I'm going to do, and so I'm just going to wing it and see what happens, okay? So again, in this article, they're arguing for central focus of our data analyses, identifying what types of values for our parameters are supported by the data and which types aren't, right? And thinking about that in a much more clear, effective way than is something different than zero, or what if something's a value that's imaginary and not actually a value that is supported by anybody's data. All right. Last thing we'll finish up with here, we won't get all the way through this, but we've sort of finished the last piece here, talking about our confidence intervals on effect sizes, okay? Confidence intervals for our means are based on a central t distribution, okay? Our central t distribution is symmetrical, centered around zero, right? When we're calculating our confidence intervals, the test statistics that we're using are pulled from our t tables for a given degree of freedom. Our central t distributions that are tabled, these are distributions determined by a single parameter, your degree of freedom, right? So all you need to know is your degree of freedom. You find your degree of freedom, and that's going to tell you the distribution of your test statistic, okay? And when we're running our null hypothesis test, we're using a t distribution that's assuming a central t distribution under the null hypothesis, right? Under the null, we're assuming that the average value of your test statistic is zero, right? Sometimes it's going to be above, sometimes it's going to be below, but assuming that the null is true, we're going to have a test statistic that's distributed around a 0 point. Okay? People comfortable with this, right? This isn't news, but just want to make sure we're good because I'm ready to blow your mind, all right? Confidence intervals for effect size, generally not assuming the null hypotheses. We're not assuming that the mean is 0. Why? Why doesn't it make sense to calculate a confidence interval around an effect size if we're assuming that the null is 0? Because yeah, like why in God's name would we calculate an effect size around 0? Like, because 0 is not an effect, right? Like, I'm not, what's the range of plausible effect sizes given that I'm assuming that the null that there is no effect, right? It doesn't make any sense. If we're calculating a confidence interval around an effect size, we're assuming that there's an effect to be had, right? That the population that I'm pulling from, the actual population value isn't 0. It's something different, right? And so because we're assuming a value that's different than what we have under the null, it requires our incorporation of that non-central t distribution that we talked about previously, okay? Our non-central t distribution, and this is the distribution of test statistics where the numerator isn't 0, right? It's the null hypothesis is something different, or the null value, or the reference value is something different than 0. Our non-central t distribution is not symmetrical and not centered on 0, right? So the test statistics that we're calculating when we're pulling from a population that's different than the null, that distribution, like we talked before in those overlapping distributions, that's not a distribution that's centered on 0. It's centered on something that's different than 0, right? And as that distribution shifts away from 0, we also start to see skew in our distributions. Okay, it's not a nice, perfectly symmetrical distribution. The distribution of test statistics that we're calculating are now skewed, and our non-central t is determined by 2 factors. One, so in order to identify the distribution of this collection of t-scores, I need to know the degrees of freedom, and then I also need to know my non-centrality parameter, or how far that distribution is shifted off of 0. Okay, and our null and our non-centrality parameter gives us an estimate of the difference between the true mean and the mean under the null, right? And again, what does this shift also represent or related to, Stephanie? Not our sample size.
No,
Effect size, right? I'm sorry. Did you say effect size?
Yeah.
Okay. Sorry. No, that's not the right answer that you didn't give me to start with, right? So this non-centrality, this shift off, this is a direct representation of our effect size, okay? And because effect sizes are a linear function of our non-centrality parameter, if we calculate a confidence interval around our non-centrality parameter, we can then back translate that into a confidence interval around our effect size. Okay? So the trick is, with what we're trying to do, is use this to calculate a non-centrality parameter. Okay? And again, Wilkinson saying that interval estimates should be giving for any effect sizes involving our principal outcomes. So if we think about our non-central t distributions, some different properties here. Non-central t distribution centered at our non-centrality parameter, which can take any positive or negative value. Okay, so we can have negative non-centrality parameters, positive non-centrality parameters. This actually ends up being kind of arbitrary if you just flip them around, right? But technically, we can have any non-centrality parameters ranging from 0 to infinity, from 0 to negative infinity. At non-centrality parameter equals 0, our non-central t distribution is equal to our central t distribution. Okay? So again, think if this is our t distribution that we know and love. As we start shifting it one way or the other, we're changing our centrality parameter, right? Because we're changing where that distribution is centered, and we're also changing the shape of the distribution. Non-central distribution is skewed very strongly at low degrees of freedom, but less so as our degrees of freedom increase. And our skew is increased with the severity of our non-centrality parameter. So if we see these 3 panels here we have a low degree of freedom, right? And we see values that are fairly skewed as we go delta 2, 5, 10 with only 5 degrees of freedom. By the time we get out to delta equal to 10, that's a really ugly distribution that's really, really skewed. But if we go through the same thing at delta 0, 2, 5, and 10 for degrees of freedom 20, degrees of freedom 60, it starts to make that skew less, right? So our skew increases as our non-centrality parameter increases. So as our effect sizes get larger, as the difference between our distribution of our t versus the null gets increasingly large, we see more skew. That skew decreases a bit as our degrees of freedom increase, but for for a given non-centrality parameter, non-central t starts to approach a central t as the degrees of freedom increase, but this is very gradual, right? So if we have, say, a non-central t distribution with, say, delta equal 5, right, our non-central t, we see at low degrees of freedom, very skewed. At more degrees of freedom, it's starting to normal out. But this is actually a process that's more gradual than what's shown here. And so even with a small non-centrality parameter, we still get some level of skew, even at relatively large degrees of freedom. So what ends up happening is this ends up being a very, very tricky. So what we need to find that non-centrality parameter, right? We need to find where this t distribution is centered at in order to calculate a confidence interval on our effect size. But the problem is, this is very, very tricky to do because I have to figure out sort of what this parameter is what the distribution is and all these types of things. This is what makes calculating, until recently, calculating confidence intervals around effect sizes very hard. Because what you would need to do is be able to program in SAS and say, all right, this is the, or R, you know, this is the parameters, and I want you to calculate with repeated estimates the effects, or the, under this distribution, here's this and here's this, are non-centrality parameters. So our confidence intervals around our means, based on a central T, our confidence intervals are symmetrical, right? When we're calculating a 95% confidence interval, we're looking at the same margin of error above and below, right? Because we're working with a central T distribution. When we start calculating confidence intervals around effect sizes, assuming a non-central T distribution, we get skew one way or the other, and so our point estimate isn't directly centered in the middle of our confidence interval, right? We may have a shorter lower bound and a higher upper bound. All of this starts to make calculating your confidence intervals around effect sizes difficult. Luckily, we have a program available, easily accessible online. Here's the link. Previously, what we had to do is use tables extrapolated from central distributions, limited number of scenarios under which those were calculated. But what we can do now very easily is go through, pop up a small little thing like this that doesn't seem like anything. It just pops up as kind of a little widget on your screen. But what we can do is very quickly start calculating non-centrality parameters for T, F, chi-square distributions very quickly and easily. All we need to do is you choose a distribution. You want to look at an F, T, or chi-square. We're working with T distributions right now, right? Choose a quantity compute. We want to calculate a 95% confidence interval. We enter our test value and our degrees of freedom, and we go ahead and hit compute. And what this does is it gives us a confidence interval, a lower bound confidence interval for our non-centrality parameter, and an upper bound confidence interval for our centrality parameter, right? So basically what we've got is a lower and upper bound limit for our non-centrality parameters, okay? It's calculated very quickly and efficiently using this calculator. And then what we can do then, right, and we'll pick this up next week. Then, once we have a lower bound and upper bound estimate for our non-centrality parameter, calculating confidence intervals around effect size is this now, right? For a lower bound for our single sample mean is just our non-centrality parameter, our lower estimate over the square root of our sample size. Upper estimate is a non-centrality over the square root of our sample size. That just gives me the sample size around my Cohen's d for my single sample test. Same thing for independent samples. Take our centrality parameter, upper and lower, multiply it by 1 over the sample size of sample 1, 1 over the sample size of sample 2. That gives me lower bound for my independent sample effect size, upper bound. Same thing with my repeated measures. These look very similar. Why is that? And by similar, I mean the same. Is that they are, right? Again, our paired sample T is just a single sample test with the different scores, same type of thing, okay? The only thing that you need to be careful of when you're calculating confidence intervals around your effect sizes, okay? What are we imputing to get our effects, our confidence intervals around our non-centrality parameter here? What's the value that we're punching in to calculate upper and lower limits of our centrality parameter? Our t-test, right? And so our estimate of our upper and lower bound for our test statistic, or for our non-centrality parameter, is determined by our t-test, right? And so if I'm going to calculate a confidence interval around an effect size, I have to use my test statistic in order to get the upper and lower bounds of the non-centrality parameter. So what I need to do is make sure that whatever I'm using is the standardizer for my effect size is the same variance estimate that was used in the calculation of my test statistic. Otherwise, what we've got going on is an apples and oranges thing, right? So in my single sample test, it's easy because I've only got one sample, one standard deviation to work with. For my independent samples, should I use glasses delta as my point estimate and then calculate a confidence interval using this procedure here around that glasses delta? Probably not, right? Because the sample of the variance of my control group isn't the variance that goes into the calculation of my test statistic, it's the combination, right? I'm using a pooled variance estimate. So what is the, if I want to calculate a confidence interval around an effect size for my independent sample test, what effect size do I need to be calculating? Or what effect size do I need to use as my point estimate? Hedges G, right? Because that's independent on sort of what test statistic we're using and things like that. But yeah, we need to use that pooled variance estimate because that's the same variance estimate that went into calculation of our test statistic. Now for these things, you can kind of fudge and get away with things, but where you can run into trouble is your repeated measures, okay? What's the variance estimate that goes into calculating your test statistic for your repeated measures T? Standard deviation of change scores, right? And so if you use average variance or something along those lines as your point estimate, what you can get is a point estimate that doesn't fall within the bounds of your confidence interval that you've calculated. Because when you're calculating your non-centrality parameter for your paired sample T, that's assuming a test statistic that uses the standard deviation of the difference scores in the calculation of the standard error. If I calculate a point estimate using D average or glasses delta, what I'm going to end up with is a sample or a point estimate that's probably going to be far lower than the lower bound estimate based on the non-centrality parameters that I use in the calculation of my confidence interval. All right, cool. Thank you so much.